Hello. Let's restart with our second lecture. I present Isa. Isa is an old colleague of mine since undergraduate studies. Isa concluded the undergraduate studies in Federal University of Rio de Janeiro in physics in 2004. After that, she participated of a program of research assistantship in astrophysics at the Johns Hopkins University, Washington, D.C., concluded in 2005. Then she moved to Holland, where she obtained a master's degree in astrophysics from the Leiden Observatory in 2007, and the PhD from Leiden and Caltech in 2011. She was postdoctoral fellow Alan J. Smith between 2011 and 2013 at the University of Texas, Austin. And since 2013, she's postdoctoral fellow Science Without Borders here at Observatório Nacional. Isa is interested in the evolution of dust in protoplanetary disks, physical structures of disks, also complex chemistry in shells of giant stars, and other topics related. Thank you, Isa, for having accepted the invitation for a talk here, entitled Dust in Protoplanetary Disks.
Thank you, Vinicius. It sounds like I accepted the invitation for myself, since I'm also the organizer. But today I'm going to be talking about dust in protoplanetary disks, which is my bread and butter. This is what I do for a living. And I hope I will be able to give you a bit of an overview of the field, as well as some of my own results, because they are just so good. So I will start saying, why is it that we do this? And the reason is because planets exist. So here we see the 8 planets in the solar system. We live in one of them. We can observe at night some of the others. So it's very, from the beginning of times, very early age, we know the planets do form somehow. I knew this was loud. Planets do form somehow because we live in one of them and we observe some of them. But already in the solar system, we can see a very big difference. Those 8 planets, they do not look the same. We, in fact, separate them into the rocky planets and the giant planets. So we see that planet formation took place here in the solar system, but already here, something very different happened between these guys and these guys. So that's already reason enough to try to understand how they form and why is it that things happen this way. But then even more than this, we also know planets outside of our solar system. So planetary system is not something that only happened once, like perhaps by chance, but it happens around many other stars, some that we can observe. So we know today more than 2,000 confirmed exoplanets, and if you consider the candidates, we have even more. And here I really like this because if you look at this for hours, you will be hypnotized, you will think of nothing else. But here we're seeing the Kepler planets discovered by until November 2013. It's an animation by Danny Fabric. And what we're seeing here are the planets and its orbits. And we see that the planets are, in each system, the size of the planets are in a scale. So you see like a big planet here and there's a small there. And the orbits are also in scale. But obviously, the size and the orbits are not in scale with each other, right? Otherwise, there would be some planets touching the central star. So we see, this is to illustrate the diversity. So there is a diversity in our own solar system. Planets that are very different, but there's a diversity out there in the universe that we need to try to understand. Why do we see such huge planets so close to the star, small planets, different orbits? I see that nobody's looking at me because you're all hypnotized. Yeah. It's online, it's on YouTube. You can put it on a loop and spend the whole day when you really need to finish your article or your thesis. This is really good. So those are the Kepler planets. So there's a lot of planets, and we want to understand how they form, what happened to them, how different they are, how likely they are to each other. We want to know what's happening. So basically the motivation is, as Fred this morning starts hinting, and I think tomorrow he's going to talk to more details about protoplanetary disks and therefore planet formation. What we do know, what we understand, what we believe we know, is that planets form around the young stars. So during the process of star formation that Fred described this morning in great details, those circumstellar disks or protoplanetary disks, so people call by both names, and you can use whatever you like. I like the word protoplanetary disk because it gives you this information that that's the place where those planets form. So the planets form inside these protoplanetary disks around young stars. But we also know by observation that at least until today, with the technology that we possess, not all main sequence stars show signs of having planets. And at least this is true for giant planets, because those are the bigger planets, the easiest, in general, the easiest to find. It's easier to find something big than something very small. So it could be that as technology advances, we find out that maybe all stars do have planets, but right now, at this moment, what we know is that not all main sequence stars show signs of having planets. So the big question, what drives my research, is to find out why some stars form planets and some others possibly did not form planets, when all stars, as we saw it earlier this morning, all stars seem to be surrounded by these protoplanetary disks when they are formed. So they all have the disk at some point, at least. So they all, in principle, they all have the material to form planets there, but it looks like not all of them form planets. So something is happening there. And to understand that, I will go back to this general scenario for star and planet formation, that as it was introduced to us this morning, Professor Adams was one of the people that first came up with this idea of this pictogram of how things happen. So we have a molecular cloud. Inside this molecular cloud, in some areas, we have those cores, those denser areas in which we believe that star formation is going to happen. And we heard all of the details of how we understand physically that this happens, how this diffuse ISM is going to go into more and more concentrated areas up to a moment in which this cloud starts to collapse. And this collapse, as we understand, is centrally. So that's what's taking place here. And I like this very much because it doesn't show what's taking place here, because that's exactly what happens in nature. So what we understand that is here, this core is collapsing to form a star, as we saw all this explanation this morning. But in reality, this is something that happens behind the curtain. We cannot really see what's happening there because it's a very dusty environment. And we have some techniques, and we learned some of those things this morning. But what we understand that takes place is that this region collapses into a central object that we call here still a protostar, because it's not a star yet. It's still contracting toward the main sequence. We're surrounded by a disk of material, a circumstellar disk that we call protoplanetary disk. And this guy is going to evolve somehow. So this protostar is going to evolve into a main sequence star, and this disk potentially into this planetary system. So the point here is that these protoplanetary disks always form. This is a way to conserve angular momentum. We even saw this earlier this morning, that most of the material, as it's collapsing, does not collapse directly into the star, but collapse into this disk. So this always happens. But the giant planets, or the planets in general, they perhaps not always form. And I used to have this, I used to be very certain. So I just, as I was watching the lecture this morning, I put this question mark here, because the truth is that I'm not so certain anymore that this is not something that always happens. But here we go. This is what a protoplanetary disk possibly look like as far as we understand. So this is an artist impression. Please don't think that this is the level of observations. We do not really know, cannot really do these movies in real life, also because this takes some millions of years, so it would take a long time. But this is what we understand. In the beginning, what we have in these disks is dust and gas from the interstellar medium, because that's the material that was there, the material that forms the star and that will form this disk. So what we see here is this protostar in the center. We see around this protoplanetary disk that is gas and dust. We assume that it's gas and dust just like the ISM, so that's an assumption that we also need to test, that it has the same gas to dust ratio, much more gas, about 100 particles of gas to dust, but the dust is the main source of opacity, so what we see is the dust, even though the dust is the minority in the system. And what we want to know is what is it that determines what's going to happen to this material. So in this animation specifically, is forming here a protoplanet, which is this brighter guy here. So what happens is material somehow gets together to form this protoplanet. And at least at the beginning, we would imagine that this would happen from the inside out. So at the close to the star, you will form the first planet, and the second, and the third, and maybe that's old view, but regardless, what determines what's going to happen, and that's what I do. So to tell a bit of the details of the things that we have learned and understood over the past few years about what's taking place in these disks, I would like to tell you a bit what is the view, the general view, the simplified view of what we understand of disk evolution. So we start here with this disk that is massive. So we have a star here, protostar in the center. So you imagine this disk that is this is a picture of revolution, right? So you have to take this guy and turn it around the star to make the disk. So this is just a cross section. And what we see here in blue is the gas, and those brownish dots are dust particles. So at the beginning, we imagine, we understand, we suppose that what we have is gas and very small dust particles, ISM-like dust particles, which are really, really small, sub-micrometer in size. And dust that is this small tends to be coupled to the gas, so it's floating inside the gas of this disk together with the gas going around the star. As times pass, we understand from observations, from theories, and also very specially, this is an interesting field in which there's a lot of laboratory work. We understand that these particles, these very small particles, they tend, the density is kind of high, and they tend to collide with each other and grow. So there's two small particles that they encounter each other while they are going around the star, and is what we call hit and stick. As they hit each other, they glue together and they form a particle that is now bigger and bigger and bigger. So this is a process that keeps taking place. And as the particles grow, they decouple from the gas because now they are more massive. And particles, dust particles that are not coupled to the gas, they tend to sediment to the midplane of the disk here. So in the center of the disk, the plane, there a CD, let's say, in the middle of this disk that is very flare, there's particles that are bigger and bigger. They are decoupled from the gas, making this an area that is likely much denser, much more fuller of material, which would in place be easier for planets to form, because now we have higher densities. It's more likely that these particles will hit other particles, stick, and form bigger and bigger particles. And as the dust is the main opacity of these disks, as the dust grows and settles, the gas now doesn't have anything that shields the gas from the stellar, the radiation from the star, winds, and they tend to also, as the radiation passes here, as is showing here, FUV photons, they sweep out of the system a lot of the gas and some of the dust. So the gas also will be kind of used up. As times pass, we also observe that some of the radiation of the star can directly photoevaporate the gas of the disk. So as time passes, the dust in these disks is gonna likely, what we want, form bigger and bigger bodies, all the way to planet-sized bodies. And the gas will either be accreted into the star, which is what's happening here, accretion, I think something that is going to be talked about tomorrow, accreted into those planets, protoplanets, or ejected from the system. So at the end, what we have is a main sequence star with some possible planets, giant, rocky, and also some relics of a planet formation, which will be things like asteroids and comets. So dust is the main source of opacity. That's important because that's what we observe. That's what I observe is important to me. In general, when the dust goes, so does the gas. And that's important for planet formation because giant planets especially, they are full of gas, so they need to form while there's still a lot of gas in these disks. Otherwise, there would be no gas for them to become gas giants. So in reality, this picture is beautiful and makes you think like, wow, great. Everything is understood, right? I just explained to you how planets form. Let's all close our notebooks and go home. Sorry for the other speakers. But the reality is that we really don't know that all of this is taking place because a lot of the stuff that happens is happening here, at least in terms of planet formation, is happening here in the midplane of this disk, where we cannot directly see, because this disk is full of dust and gas. So the opacity of the dust makes it such that we are trying to find out how planet formation works, since we know that it's happening right outside of this wall, but we cannot really directly look through this wall and see what's happening there. So it would be great to know exactly what these disks are made of, what kind of dust there is there, what kind of gas there is there, what is the dust and the gas are doing in the surface, in the midplane. But we really don't know. We cannot yet observe all of this because the observations do not penetrate this far. So we settle for the next best thing, which is what astronomers do in general. We look at what is it that we can see, and we just extrapolate for what we cannot see and make a beautiful picture here that you can tell your mother when you get home, oh, I know how planets form. So what is it that we observe? We are going to settle for the next best thing, which is what we can do. And what we can do is that initially, these young stars with this, so here we have a pictogram of a star and a disk around it. These guys are very easy to find in the infrared because stars in general, so here's a spectral energy distribution. It was promised that there would be spectral energy distributions, so I guess we're going to learn more about that tomorrow. So the spectral energy distribution of this system here, and if you observe in the night sky, a main sequence star, all we're going to see is something like a black body, to a first approximation, a black body radiation here. So this thing here is the radiation of the star. And if you were to observe any star out in the sky, this is what you're going to see. The peak, in which wavelength here the peak happens depends on the temperature of the star. There are several things that you can learn about stars, not my field, but this is what you're going to see. And then in the infrared, what was observed is that the guys were expecting to see a protostar, which is just this, and what they saw in turn was a spectral energy distribution that is this guy here. So there's a lot of excess of radiation on top of what we would expect. If it were only a star, this is what we're going to see. So everything that is here is what we call excess, infrared excess of radiation in infrared wavelengths. And that's how we infer the presence of disks, because as we see here, this disk does not have its own source of radiation. It receives the light of the star and reprocesses this radiation and re-emits at wavelengths that are longer because they're colder than the star. So when there is excess of infrared radiation in young stars, we assume that there's a protoplanetary disk, there's a disk there. And if we do some math, some radiative transfer, we directly can, assuming some things, assuming what the dust is, what the gas is, we can derive some correspondences between the geometry of this disk and what we are observing here. So in this case here, there's a lot of excess of radiation in the infrared, meaning that we interpret that there is a very big, full flare disk. And this is going to be important in the future. So when we observe this is what we see. And here I like this figure because it shows a bit of in which type of wavelength regime we can observe what. So at the beginning, before now, we have a lot of millimeter observations, so we are starting to penetrate within the disk and observe what's happening in the midplane. But until maybe 10 years ago, most of what we saw was here the surface of the disk, because this disk is very opaque when we observe in the infrared or scatter light. And what we understand that is happening inside the disk is a combination of things. So as I said, this dust is going to hit each other and potentially grow into bigger and bigger particles. So when this happens here, the bigger the particle, the faster it's going to settle to the disk midplane. So we're going to have, there's a different, so that's number 2 here, vertical settling. There's turbulent mixing in this disk, and I'm going to go back to this, so how we know. So the material tends to go sediment to the disk midplane, but also some material tends to come back up, and we're going to see that. We have a problem of radial drift, which is a big problem for planet formation, because when these particles reach a size, usually the canonical size is about 1 meter, they tend to spiral really quickly into this star, and then they are lost. So we cannot really pass this yet, but it happens in nature. And also this collision, this hit and stick, not always is constructive. Sometimes two particles, they hit each other and they stick together, but sometimes the velocity between them is very high. This can be a destructive process instead of constructive. So you're trying to grow these particles to make a bigger and bigger body into potentially a planet, but sometimes the same process of construction breaks them apart, creating new small dust. And all of this is important. So a very important thing about disks is how long they last. Because if we're going to form planets, and that's especially true for giant planets because they have a lot of gas, they need to be formed while there's still gas in the system. So from infrared observations, and those are the early, most of what we know in terms of statistics is still from the optical and the infrared. The millimeter era is still kind of starting. So what we see here is disk frequency. So basically it's the percentage of stars that still have disks in a cluster, in a certain region. And here's the mean age of that cluster, of that region. So what we would expect is that at age 0, 100% of the stars have disks because the disk formed together with them. And at some a main sequence, 0% of the stars have disks because the disk has dissipated. So we start looking. So you take an image of a cluster or star-forming region, and you look for this infrared excess, this signature of disks. So that's why it's important to know that this is from infrared observations. And we see here that about 1 million years, maybe 80 or 90% of those stars still have disks. And maybe by 5 to 10 million years, less than 5% of the stars have disks. So we have some constraints here on the time that it takes for the majority of this disk to dissipate. So as we can see, obviously, this is not something perfect because otherwise it would be 100% and then 0 would be a binary. If this was like 10 million years or 5 million years, it would be all the stars have disks before and all the stars don't have disks after, but we can have an idea. And the constraints that we get here is that giant planets that need gas, and possibly the embryos of the terrestrial planets, because this is a process that can continue, and I think we're going to hear more about this, they must form within this time here in which the majority of stars still have planets. So what is it that this number is? Depend with who you're talking to. Some people say 2, 3 million years, some people say 10, but we do know that it is a few million years. So they need to form. And this is a major problem for people that do theory of planet formation, because you need to go from something very small into something very big in a time that is quite short. So we're going to talk about this. And if nothing else, if you were asleep before or will fall asleep after, so bear with me in this slide. I think this is the most important thing that I would like to tell you today from people that work with dust, such as myself, is that this is the problem here that we are dealing with. We start with dust, that's what we have in the ISM. We want to finish with planets. We don't know if this is always going to happen, but this is what we want, so let's be optimistic and go for our goal. We want to form planets, and how is it that we understand what's happening? Well, really small dust, this type of millimeter, sub-millimeter, up to micrometer, sub-micrometer, up to millimeter in size, we can directly observe. We can observe those guys directly in the infrared, in the millimeter. So this is what people like me do. This is what I do for a living. Observe what's happening here. And I would like to observe what's happening here, and here, and here, and here, but I can't. And it's not because I'm not a good astronomer. Nobody can. This is not something that can be done. We cannot directly, there is no techniques to observe around a star that is 100 or 200 parsecs from us, a body of about 1 meter in the midplane of the disk. Not that I know of. Fred's looking at me very skeptical, so I think he might tell us something that I don't know, but...
No, I agree.
So we cannot really observe these guys, but then we can observe these guys. At the other end of the spectrum, we can observe planets and we can observe exoplanets. So we know that this happens here, but we just don't, we cannot see directly. Cannot trace the steps and say, this is happening, this is happening, this is happening. We have some very good restriction from the solar system, because we can actually even have solar system material in our hands in our labs and study them. But it's one object. This happens 4.5 billion years ago. It doesn't necessarily reflect what happens every time. And then you think, oh, great. Then what we do is what we always do. We use models to bridge this gap. Well, that is a problem that I'm going to tell you in a bit, is that there's nobody that I know that is able to do this. So it's a big problem. We cannot observe what's happening here, and we cannot really model directly what's happening here. So there's way too many open parameters, and that's what we're talking about. So what we know from dust to planets is a modification of the dust and the gas. Gas is very important. I don't care very much, but it's very important. So don't go out thinking that dust is all that there is. So it's a modification of the dust and the gas inside these disks that give rise to planets. It must happen within a few million years, and is a process that may or may not occur all the time. So far I would say it doesn't occur. So let's talk about theories. How is it that theoretically we form a planet? As I said, until now, nobody is really capable of forming planets from dust theoretically in their computer. There's no one model that starts with dust and finishes with formed planets, a planetary system like our own or any for that matter. So the simulations in general, they are divided in two types. There's the people that start with the ISM, start with dust and gas, and form planetesimals, and then they reach a very big problem, which is, I had already touched on it, is that when these particles reach maybe 1 meter to kilometer size, these particles, they feel a radial drift, and they very quickly, 10 to the 5 years, they spiral into the star and then they are lost. So you're forming a lot of planetesimals, but you can never go from these planetesimals into a planet. This just is not possible yet to be done. And there's the guys that say, well, I don't care. I don't care how these guys formed. So they already start with a disk full of kilometer-sized particles. So these guys, they no longer feel this drift inwards. And then you ask them, how did you form the kilometer-sized particles? They don't care, really. They don't know and they don't care. They just assume that you start with that, and then from that you can form planets. So there's two different groups, and in the middle there's nobody because just physics does not allow this. The main theories for planet formation is, as already explained, I would say as a dust scientist, the coagulation of smaller particles into bigger particles is the main way to form planets. So you will slowly build up a bigger and bigger and bigger and bigger and bigger particle until you have something the size of a planet. But there is a competing theory that has a lot of pros, which is called disk instability. In this theory, a planet forms very similarly to how a star forms. So in a region in the disk has an overdensity, that there will be a Jeans mass for planets. So there will be a moment in which the density is going to be high enough that this region of the disk will collapse and form already a big planet. So that would be a way to quickly surpass this meter-sized barrier, because you would already form a planet that is bigger than the size that's spiraling into the stars. But obviously there's other problems with this theory, and I will list here. So one of the main problems is the lifetime of the disks. Is a problem especially for this coagulation theory, because as you can imagine, if you start with sub-micron sized dust and you want to stick two in pairs, pair collisions, so 2 and 2 sticking together to form things that are going to get from sub-micron size to thousands of kilometers in size, that takes a long time. And we see that these protoplanetary disks, these gaseous disks, they last a few million years, so it's a problem. Another problem is the mass of the disk. So to get to the theories that do this disk instability, you need to have a disk that is very massive for the instability, for you to have an area that will collapse under its own gravity and form a planet. And in general, those theories, they demand disk masses that are higher than what we observe. So it's possible that something is still missing. And of course, I already touched on that. It is a big problem that planetesimals tend to migrate very fast into the star, so they get lost. And if they are lost, you cannot form a planet from there. So what we're at, we have external processes for these disks, things that have been already touched on this morning: accretion from the disk to the star, stellar winds that can sweep up some material out of the system. We have photoevaporation. We have the presence of a companion. That's why I asked the question this morning, because we do know that the majority of low-mass stars form in multiple systems, not in one star isolated, which is that beautiful picture that I showed you of the disk. In general, the stars have a companion, and we would like to know what is it that this companion does to this system. And this is the only study that I know, but it's very interesting, from Krauss et al. In Taurus, Taurus is the prototype for star formation because it's a region that is very close by and there's very little extinction, so we can do a lot of studies. So he and these guys, they studied the multiplicity of stars with disks in this region. And what they show here is that, so this is the single stars. Taurus is about 1 million years old. So about 80% of the single stars at that age have disks still. And they see that for the close binaries, at the same age, something like between 20 and 50% of the stars still have disks. So what they are saying is that, and for wide binaries, is the same as single stars. So what they are saying is that the disks for 2/3 of these guys dissipated really quickly in 1 million years, super quickly, and that could be a possibility of why planets don't form around all stars. Maybe some of the stars that have these disks that dissipate very quickly is because they have a binary, a close binary, that as it passes around, it disrupts this disk. And also, of course, we have the internal processes, which is the evolution of the disk. So these are things that happen to the disk, and these are things that happen within the disk. That is what we need to study. Oh, I talked too much, I'm so sorry. Let's move on. So I'm gonna separate dust in two ways as things that happen within the disk. We're gonna talk about dust as observed in the infrared and dust as observed in the millimeter. So in the infrared, this is what I have done most of my career, because I am older than you guys, from my era, pre-ALMA era. So most of my results are here, but keep in mind, in the infrared, what we're looking at is the surface of the disk. In the infrared, the extinction is too high, we can never see what's happening inside in the disk midplane. But it can be a good tracer for the gas behavior, because this small dust is coupled to the gas. So most of the results in the infrared came from Spitzer Space Telescope. I hope that all of you have heard about it. Of course, there has been infrared observations before. There has been infrared observations after, but Spitzer had a differential, which is it was able to map large areas, so we could get a lot of data into a lot of star-forming regions, clusters. So we have data on thousands of young stellar objects observed. So we have statistics that we could start learning some things that always happen. So this is a lot of what I did. So I used the spectrograph in Spitzer, that's called IRS. And here are two examples of this spectra. It goes from 5 to 35 microns. And it is very important for the study of dust, because dust particles, they emit at 5, so we assume that a lot of this dust, and we do observe, is silicate dust, just like sand. So it's a form of silicate material that has two bands here in this area, so we are able to directly look at the spectra of this dust and see what is it that is doing and what is it that is made of. So it was very important to try to understand at least what's happening in the surface of the disk. So we have a spectra for hundreds of disks, so we can get some constraints on the structure of the disk, because I already told you that the amount of infrared excess can, at least we assume that the amount of infrared excess can give us a bit of information on the morphology of these disks. And it can also, because of these bands that we observe, also PAHs, it can give us some information on the physical and chemical processes that are taking place in this disk, at least in the upper layers of the disk. So I worked a lot with Serpens, this is my little baby, because I had a complete and unbiased flux limited sample. So for Serpens, basically I had all the data that there was available from UV to the mid-infrared for all of the young stars with disks. So I could directly look at these statistics and see what is it that we see that is happening for all the disks, or happening for some disks still. And the first thing that I would like to take home from this is that the incredible diversity of disks in Serpens. We do not see, so Serpens, we assume, and we can have this conversation whether this is good or not, but we assume that it's coeval, that all the star formation took place, more or less at the same time, so that all those stars have more or less the same age. And then, naively, you would expect that all disks look more or less the same. Like little children, if you look at a kindergarten class, if they all are 3 years old, they're kind of like the same height. And all the 4-year-olds are kind of like the same height, which is a bit higher than the 3-year-old. Now, time is very important for height at a young age. But this does not happen for disks. We see disks that are very full, a lot of infrared excess, so there's a lot of material, all the way to disks that almost don't have any infrared excess and have already dissipated most of the disks. So incredible diversity. And that brings us to the first conclusion that we learned from the infrared, from doing spectral energy distributions, which is what we're seeing here. Again, this dotted line here is the black body of the star. So what we see on top of it is the infrared excess, so that's what comes from the disk. So the fact that we see stars that have a lot of disk, so we do just some a flux ratio of 30 and 13. So if this is flat, if this flux ratio is flat, it means that this disk is flare. And if this flux ratio is already very small, it means that this disk is flat. And we see a lot of flared and a lot of flat disks with the same age. So the first conclusion is that, assuming that this is coeval, time is not the only parameter that drives the disk evolution. Otherwise, if both those stars are 1 million years old, you would expect them to have disks that are very much alike, that look the same, either a lot of disk or very little disk. So there's something else besides time. Even more than that, we can look for stars without disks in the same cluster. So there's other techniques to find stars without disks. We do here looking at the X-ray, because the young stars are very active in the X-ray. So we look for stars. So here in black, we have the stars discovered by Spitzer, that have infrared excess, that have disks. And in red, the stars that were discovered in the X-ray, so they do not have disks. And we wanted to see if there's a difference in mass or in ages of these stars that would justify the fact that these guys in red no longer have disks. Maybe they are already older, and then they already had time to dissipate these disks. That's not what we see. Or maybe they are more massive. We know in astronomy that in general, more massive stars tend to go through life much faster, and it could be that that drives their disks evolving much faster, and that's also not what we see. So the presence of absence of disks does not seem, at least in serpents, to be directly correlated with the stellar mass distribution or the age distribution. We also compare with the intermediate mass stars, we call Herbig-Abe stars. So those are intermediate mass stars, they still have disks, and the stars that I've been talking about so far are T-Tauri stars, so low mass stars with disks. So this is known for a long time. That's intermediate mass stars, so the ones, the flared ones and the flat with disk and without disks, they have a very discrete, different distribution of luminosity. If you have disks, the luminosity is much higher than if the disks are flat and almost dissipating. Kind of a bimodal distribution, and we wanted to see if that's true for low mass stars, but as you can see in this distribution between flare and flat, we do not see that. So things seem to be much more complicated for low mass stars than for intermediate mass stars. We use this this spectra, as I said, they have from 5 to 35, so they cover 2 silicate bands at 10 and 20 microns. And from the ISM, what we knew is this purple one here and this blue, these very peaky, strong silicate features. And then in disks, this is the kind of thing that we observe. A lot of different shapes and strengths of these lines, and we wanted to understand why. So we go to the laboratory, and this is what laboratory data combined with models give us, that if you change the size of the dust that is emitting this spectra that we are observing, we change a lot the strength and the shape of these features. So we see, oh man, we are observing grain growth. Whoa, super cool. So let's do something, and we try to as scientists, to put numbers on everything. So we're gonna see for hundreds, thousands potentially of spectra, we're gonna see how strong this line is, so that's S10, the strength of this line, and we're also gonna measure the ratio of these two things. So if the particles are very small, the ratio of 11 to 10 is going to be very small. And if the particles are big, this is going to be almost unity. So this is something that you can quickly apply to a lot of data and have some quantitative results. So this is what I did for serpents. Here's serpents in black. And you see, oh, cool. So here's ISM-like dust, very small. And this is the last one here is 6 microns, so has already grown quite a lot. And I said, man, that's so cool. We are seeing dust growth here. We see particles that are no longer like the ISM. Super excited, you write an article, you feel very good about yourself, and then you think, wow, does this always happen? So
why does 11.3 mean? The size?
Is this a ratio here that tells us if this is very peaked or if it's very boxy-like? Sorry. Is this the ratio between these two here? If this is small or big? So it just tells us if...
the wavelength.
Yeah.
Yeah, okay.
So let's do this first. So I was serpents. It was very annoying about serpents and people saying, oh, is that representative at all? So I decided to look at some other regions, and We always do Taurus because Taurus is the prototype and there's a lot of data, but I decided to look for some regions that are also older. So here we have in blue Upper Scorpius and in green Ithaca Meleontis, which are clusters that are already 5 to 10 million years old. So the majority of the stars in these clusters no longer have disks. And we thought, what if we look at the disks that survive? So a 6 or 8 million year disk, 8 million year disk will have, in principle, dust that is much bigger than a 1 million year disk because it had time to grow. So we do that same play, and this is what we see here. And here we see the mean values with 15 to 85 percentile error bars. And good, really no. We do not see an evolution, a direct evolution that says, look, the old guys have bigger dust than the young guys. There was more time for dust to grow, but dust doesn't seem to be growing. I repeat, what we're looking at is the surface of the disk. We really don't know what is it that is happening inside. So the difference in mean age is not reflected in the size in the surface of the disk. What we understand here is that there's an equilibrium of growth and destruction process. I already told you that particles not only grow, but they get destructed. That is necessary to be taking place all the time in the disk midplane, such that we still observe micrometer-sized dust at 6 or 8 million years. Now, in 8 million years, micrometer-sized dust should already have grown into bigger dust. So if we're still observing it, it's because it has been created, replenished. We also look at the difference between environment. We want to see if stars that are very close together and stars that are more isolated in the same region, in serpents, if they behave differently. And we don't really see it in the cluster, in the field, so both the ratio, the geometry of the disk and the size of the dust does not seem to be very different. So nothing points to really like, yeah, we are seeing growth, something taking place, evolution taking place. It looks like it doesn't matter what we decide to look for, is always the same. If the disk is very big, if the disk is very small, if the disk is very young, if the disk is very old. So it's quite of a bummer, because at the end, that was my PhD thesis, that kind of says, look how fun, we did all this, and we find out that nothing changed. So environment doesn't play a role. We can also look at, I have already said that dust composition, not only we get to see the size of this particle that is emitting in that spectrum, we can also see the composition, if it's very amorphous silicates or crystalline silicates, because that is important, especially when you're looking at the solar system, because we have very complex with objects with high crystallinity, and we don't see that in the ISM. So this had to happen during the formation of these bodies. So this is what's happening here. Crystallization happens at a high temperature, so we can also try to understand something of the chemistry that is taking place. So we take the opacities of these silicate features that emit at this area. So we have 3 amorphous guys, olivine, pyroxene, and silica, and 2 crystalline, forsterite and enstatite. As you can see here, there's the opacities for different grain sizes to try to see what is it that is emitting. So basically what we do is mix these guys together and try to match with for each observed spectrum and see what is it that we can tell from this spectrum. Basically here we have any given observed spectrum. We take the continuum out. We have a warm component, so we mix at a higher temperature all of those opacities until we match precisely this observed spectrum. And then we know how much, the code tells us how much material came from there. And then we do again, and then you cannot do the entire spectrum with one temperature. You need the second temperature. And the final fit, which is this green, usually reproduces the spectrum very well and gives you the program, the code spits a table that says we use 20% olivine of 0.1 micrometer, 5% pyroxene or 6 micrometers, and it tells you what is the composition that it was necessary to create this spectrum that we observe. And then we did this for serpents, taurus, and now we put together the 2 older regions because they have very little objects, just to make volume. And we don't, again, as we had already seen, there is not a difference in mean grain sizes as you go from 1 million years to 6 to 8. But there's also not a great difference in crystallinity fraction, which is something that we would have expected because we see the solar system. So what we see here basically is the crystallinity. We started here with ISM, and we are going to finish with crystallinity fractions that can go anywhere between maybe 10 and 80%. and sizes, I don't even need to tell you. But what we see while the disks exist is that no evolution can be seen from the surface of the disk, which is a real bummer, but we do get some constraints. So when equilibrium is reached very quickly, because in 1 million years, you already see here that whatever has to happen, happened, and this equilibrium lasts until this disk dissipates. So if planets are forming in the disk midplane, there can be no such equilibrium in the disk midplane. You have to grow bigger than micrometers, you have to grow meters, kilometers, thousands of kilometers. So the bummer conclusion is that very possibly the dust at the surface of the disk is not a good tracer for whatever is happening in the midplane, which is what we would like. We would like to say, oh, if you look at the surface that is doing this, we know precisely what's happening inside, because that always happens together. Well, unfortunately, that not seems to be the case, as it is usually the case, because the easiest thing is never what happens in science. So the picture that we have is that dust grows, of course it grows, if it has to form planets, and sediments to the midplane. Here in the midplane, you start having an environment that is really dense, so there's a lot of particles there, and the denser it is, the better it is for this dust to encounter all the particles, stick together to grow, but that also can produce fragmentation, which is going to form small particles, because there's turbulent mixing. This small dust population that is created in the midplane is brought up to the surface of the disk, and we observe this at all times. So, and this is interesting because it's a scenario that is consistent with the evidence from the solar system when we see in the meteorites that small particles came after some bigger particles. This is something that we can see in the lab, so it's not inconsistent what we're seeing. And then let me move to the millimeter, which is a bit more exciting, not only because it's new, but because we're probing some different things. So what we keep in mind now is that we can probe deeper into the disk, but we still cannot see these guys, the meter size, kilometer size, that we put at the protoplanets, we still cannot see, but we are going further. And now with ALMA, which is the revolution for this field, we are finally being able to overcome some of the resolution problems, and we're starting to get some information that is quite exciting. So when this started, I remember when this first came out, I was in this conference that this happened in 2007. So this is observations with a sub-millimeter array in Hawaii, which is obviously much smaller and less strong than ALMA. But this is Lick Alpha 330, is a protoplanetary disk. And people are really surprised with this, because what we're seeing here is millimeter-sized dust, and it's not in the entire disk. So we see here in black, there's no material. So in this cross in green is where the star is, the protostar. There's no dust close to the star. So there's a gap, there's a hole inside this disk that people got really excited. So there's an inner hole of about 40 astronomical units, and people got really excited because, of course, that hints that we are seeing planet formation. The first idea was that a planet formed here, one or more planets. It ate up all of the material around of the disk. It accreted into itself, getting bigger and bigger, and then there's no more dust. There's no dust left within 40 AU to be observed. People are really excited, like, yeah, so that's 2007. We're seeing planet formation happening, even though we're not seeing it. It's really, really cool. Even more than that is that this directly connects to what I already talked about, the spectral energy distributions. What we see, a spectral energy distribution of this guy, the ones that I had showed you before, they were like this. So there's a lot of infrared excess. There's dust everywhere. This guy does not have a lot of excess here, close to the star. So we were seeing from the millimeter precisely what we saw from the infrared. So, oh man, we cannot really see a lot of stuff from the surface, but we can tell a lot of things that are happening in the disk. We can see disk geometry directly from the infrared. People were super excited. Oh, infrared's not that bad after all. And then all the people thought about at this time was, oh man, ALMA. ALMA is going to save us all. ALMA is the second coming of the Christ. It's going to be, nothing is going to be unanswered after ALMA. So let's just wait for ALMA, because it seems like we patted ourselves in the back. We have a good handle of this. We know what's happening. Let's just wait for ALMA to get resolution. And then ALMA came, and big surprise. So here, there's two disks. This is a Herbig AB B star. HD 142527. This is a T-Tauri star, so intermediate mass and a low mass stars, both with disks. What we observed before in the infrared was this disk that is nice, well behaved. There's dust particles all around. It's a nice disk. This disk has an SED like we had seen before with a lot of infrared excess. And here in orange we see from IRS-48. And then we observe with ALMA, we expect to see a similar thing, like we had seen here, that the infrared matches the millimeter, and that's not what happened here. So we see this is the dust continue from ALMA in the top, and we see that there's not a nice, smooth distribution of millimeter particles all around this disk. The millimeter particles seem to be concentrated in one area of the disk. And I'm like, Jesus, we finally think that we learned something, and comes ALMA, they're supposed to confirm everything that we know, and shows that obviously there's a lot of things that we don't know. So what's going on here? Why isn't this millimeter particles distributed around the star as we would expect, is rotating? So we're still trying to figure it out, but the idea was introduced this concept of dust trap. So again, people get very excited because for this to work, we need a protoplanet here. So there's always this idea that we are, even though we cannot see this protoplanet, we infer that it's present. So we're always trying to find out a way to say we are seeing planet formation even though we cannot see it. So this planet would trap a lot of dust. So we see the small dust is still distributed around the disk everywhere, but the big dust is particularly in one direction. People tend to talk about horseshoe shapes. So this is still something that modelers, theoreticians are trying to understand. How could you trap this dust here? But if that is indeed possible, that is very good for planet formation, because now this area is super dense. There's a lot of material here, so it will be very easy to form a second planet here, and then a third and a fourth. Still, things are still coming, but that is the general idea. That's not all that ALMA showed to us as a surprise. This is one of the prettiest images coming out of ALMA. This is HL Tau in Taurus again. And what we see here is a face on disk. And in the infrared, we see small dust distributed in the entire disk. But in the millimeter, we see these rings. So this dark, the lighter it is, the more millimeter dust there is there. And the dark parts, it means that there's no dust, millimeter dust in those rings, in those gaps, which again is what we always say, what we always bring it. What we are seeing here is potentially planets that were formed. So if you have a protoplanet here, as this protoplanet goes around the star, it eats up, accretes all of the material in that orbit, and then we can see this one has 1, 2, 3, 4, 5, 6, 7. Man, we are seeing potentially 5, 7 planets forming, and again, there's absolutely no confirmation that this is what's happening. We need to study and try to understand what is it that is happening, but the truth is that before we had millimeter data, we'd never seen such a thing. So it's very interesting, but ALMA is still new, and there's still too few disks, and maybe those disks are special, and they are not representative of how planet formation will always happen. So what we need now is this new ALMA era, in which we are no longer observing one object here and there. Yes?
Just a question. Can you explain what else would produce that image? Would be temperature gradients and this?
This HL?
Yeah, what else could it be beyond planet formation?
I'm not sure if I would be able, but it could be, sure, it could be planet formation, but it could be just, yeah, I don't know what is it that could
Chemical
create.
gradients. That could be planets.
Huh?
Okay.
Chemical gradients.
Sure, they could be, yeah, they could
And then
be,
you get ready to transfer effects on the different.
they could be different things taking place. Always, because that's what always happens with us, that we think, oh, it's a planet, right? Because that's the most exciting answer. But usually in nature, what happens is not the most exciting answer. You see, Kokotau, the first time that we saw this type of SED, this type of behavior, that people say, and this type of hole here, man, there is a planet happening there. But now we know that for this to happen, there could be photoevaporation, there could be a small companion, a brown dwarf. So there's other things that sometimes you don't even think about it because we're so there into, oh my gosh, this planet. And what we need is really to continue studying and probing different things. This is not precisely what I do, but the idea that there's something that we've never seen before is very exciting, because you get one answer and you get 10 questions that, what is it that is happening? But it still stays the question, does this always happen? are all this kind of things happening to all disks, and we only saw a few because we only observed a few in the millimeter, or these disks are very special, and this is not what happens to all the disks, and therefore not necessarily the only path for planet formation. And now these type of questions are going to start to be answered because we're doing surveys with ALMA. So now we are starting to have this type of image, but not for 1 or 2 or 5. Whereas we like to say, we're no longer collecting butterflies. These guys, this one is pretty, this one is pretty, oh, that one is so colorful. We're now doing evolutionary biology. We can look at a bunch of them and see what is the average, what happens all the time, what never happens, what only happens. Are there different types of disks? No, we have different types of galaxies, we have different types of stars. Maybe there's different types of disks, planet-forming disks, and disks that from the beginning will never be able to form planets because they already have something that we identified. So we're starting to do this. So I'm part of this ALMA survey group that we observe 89 disks now in Lupus. So we have here a few of them, and we can start doing both the detailed study of each one of them and see what are the explanations for each one of these observations, but also we start doing statistics and see what happens all the time and what doesn't. One of the most important things about doing millimeter observations is to get dust mass. So we can know how much mass in millimeter is in the disk. So here are just all the names of these disks in Lupus. So it doesn't mean anything, it's just weird names. And they have been ordered by dust mass that we calculated from the ALMA observations. But we can also use some isotopologues of some molecule, like CO, for instance, and try to get gas masses. Because so far, and I told you from the beginning, we assume a gas-to-dust ratio of the ISM, that is 100 to 1, but there's nothing that says that this is necessarily true. It was just an assumption, but we are starting to see whether this is really true or not. So this is the gas mass, and there is dust to gas. There's still a lot of upper limits. We're still beginning to do this, but we see that it's not. This is the ISM here, this line, 100. It's not always the same, and we can start seeing whether this started from the beginning, or this is a sign of evolution. What is it that we are getting there? Oops. So the point here is that with ALMA, and in the next couple of years, if you come to Astrobion 3 or 4, in 2 or 4 years, maybe we're going to have results that are very different, because now we have millimeter ALMA resolved observations of hundreds of objects. So here's a continuum. This is 13CO and C18O that gives us some information about gas and gas masses. We're starting to really tackle what we have done for disks in the infrared, thanks to Spitzer. We're starting to do in the millimeter, thanks to ALMA, and we can put those things together and try to understand a bigger piece of this puzzle. What is it that is happening? So just to summarize, I think I'm already too long anyway. Disk evolution is complicated. It's really tough. Whether or not you're going to form planets, a lot of stuff happens that is really complicated, which is good news for students because there's a lot of work still to be done. Not what we always think like, I solved the field. There are a lot of things to do. Understanding the dust evolution is complicated because we always have incomplete information because there's a lot of things that we cannot see happening. Understanding planet formation, there's steps that are completely invisible to us. So multi-wavelength data is key because we can start probing different things and putting these things together, but still we cannot see everything. This is a very interesting field for people that like all sorts of things because we can do observations, we can do theory, and we can do labs, like laboratory experiments like you almost cannot do in any other, very few fields of astronomy. We can do laboratory experiments of dust growth. So there's people whose profession, whose job is to throw a dust particle into another and watch what happens. And they do different sizes, different velocities, and they watch what happens. Look how fun. You can spend your life throwing balls of dust into other balls of dust and observing what happens. There's also a lot of chemistry, which I didn't talk about, but there will be talks about this. There's a lot of chemistry we can know from observations and lab data. We know that from the disk surface, which is the majority of the data that we have so far, there is an equilibrium of growth and destruction process that is reached very quickly within 1 million years with a disk that is very full and that lasts until this disk dissipates. For bigger millimeter disks, so far we have seen a lot of asymmetry that could be traced in planet formation, but it could be some other things. But the ALMA era is just beginning, so there will be a lot of new exciting results that will be able to start putting disks into some sort of evolutionary sequence. So thank you very much for your attention.